Hey everybody, see we're now live. Do a Chem 103 lecture here, the latter part of stoichiometry here in a moment. And just like the previous videos, I will be time stamping when we actually start the lecture into the comments below if you're watching this after the stream. So, alright, let me just check in the Discord. I'm also going to refresh my channel if I can get a link for you guys. Looks like it is starting. If I can get a link for you guys. Looks all right. All right. We're going to get started shortly. So with this particular class, I notice you guys have not been here for the stream, but the video itself is getting about as many views as people in the class. So I'm hopeful that everybody's watching. No, I'm probably talking to the wrong people here, but for those that aren't watching, they are still responsible for the content. All right, let me just go ahead and get my setup here ready, and then I will get started. Should mute my phone as well. Just like in class, right? Gotta mute your phone. Right, and boom. And I also figured out how to do the memes. You guys seeing the meme? All right, there we go. There's our meme for the day. How's the lighting? Lighting looks okay. Yeah, I'm sorry I got a big glare in the background here. It's on this side actually, so unfortunately there's a window right above me letting in light and I can't reach it from the second floor to cover it. So bear with me with the bad lighting in the background during this. All right. So I think I'm just going to go ahead and get started here, guys. Just get this. I'm actually not planning on a very long lecture today. Normally in class, what we would do on today would be just a bunch of practice, and I would honestly would have did group work today. I would have had you guys bring the worksheets to class. I would have told you guys on Monday to do that, and then I would have did a few problems, and then set you guys loose to work with each other to practice, and then we know we have our quiz and exam coming next week. We'll talk about that at the end of the stream. So. All right, so let me go ahead and switch my view here. So go ahead and take a look at the PowerPoint again, see kind of like where we're at and then where we're going. All right, so file, oops, wrong file. It's showing. I haven't updated my setup a little bit here. Trying to get fancy. And oops, and I want this view. All right, so last time I went to stoichiometry. That's basically the mass balances in chemical reactions. And some of the stuff that we looked at here, we did a lot with this whole making pancakes thing. Remember that in actual chemical reactions, we use mole coefficients to make relationships between everything. And we did a lot of examples of pancakes, and I think I ended doing some real problems. So today's lecture is going to focus on real problems. I still wanted to go over enthalpy, heats of reactions as well as part of today's lecture. So without further ado, let's go ahead and switch over to the worksheets. So you guys should have access to these. These are on Canvas. The first one I'm going to look at is, hang on, let me switch the view again. There we go. So this is activity 3.1, I believe. Let me double check. Yeah, activity 3.1. This one had your reaction balancing. And as I mentioned last time, the stuff from this chapter is kind of all mixed together a little bit between the last two chapters. They're really kind of one chapter, to be honest. Part of also what I want to do today, excuse me, in today's lecture is I want to, for a lot of the problems, I'm going to add this extra layer. And this extra layer that I'm showing you guys is a mixture of stuff that you're going to see next semester in Chemistry 121, as well as stuff you're going to see later in this class. And I'll specify, like, hey, study this part, this part's later. I'm showing you an example on where these problems kind of go after the part that we're doing. So the first one I want to go ahead and take a look at is, oops, I think I need to flip my view on that bottom camera there. Hang on, let me do that real quick while I'm seeing it. So, hang on, layout. I'm pretty sure I can do this while being live. And I think that view is now correct. Let me see. Yep, that view in the bottom is no longer upside down. All right, so the first one I want to go ahead and do and take a look at is the one with the towards the bottom there. It says sodium phosphate and calcium chloride. This particular problem type had you guys doing a double displacement, predicting solubility, and then writing a reaction, the Ionic equation. So I want to go ahead and do all that with this one, but I'm going to add the extra layer to it, and we're going to have some stoichiometry problem to go with it. That includes concentrations. Oh no. All right, so let me just go ahead and write this down. It's sodium phosphate and calcium chloride. So I think the lighting is okay there. Sodium is Na+. Remember, we can use our charges here to help keep track. And let me just go ahead and switch over to the presenter camera now. All right, it was sodium phosphate. Sodium is a 1+. We get that from the periodic table. Phosphate is a PO4, and it is a 3-. And we can use the cross method to figure out how many of each that we need. Looks like we're going to need 3 sodiums to balance this out. So go ahead and put a 3 here. No parentheses required. This is a sodium salt, so we should have, actually, let me, I had this thing here set up. This here, it's going to be the meme, but I'm going to switch it over to the solubility chart. Let me minimize this one. This should work. Yep, there we go. All right, so you're going to need the solubility chart for this problem. Remember, I would provide this on a normal quiz or exam, and you guys definitely should have it available for the online stuff when you guys do your homework or when we get to the quiz that we're going to do. So let me just shrink this. Oh, dang it. Click on that, and then there we go. So I'm going to have this at the ready. All right, so back to the problem at hand. Sodium salts are typically soluble. Remember, phosphates are typically insoluble, but we have the exceptions of the alkali metals. That way the charts are consistent. So AQ. And I believe it was calcium chloride was the other one we were working with. Let me just double check. Yep, calcium chloride. This is calcium and chloride. You look at the periodic table, we can see that calcium is a 2+, chlorine is a 1-. So it looks like we're going to have 2 of the chlorines. Halogens are typically soluble. You then look for calcium being an exception. I'm looking at the top part of the table here. Yep, so you can see my mouse on there moving. We were looking around right here. We don't see calcium on there. This is aqueous. Remember, when they're aqueous, they break apart into solutions, so they have chances of running into each other, effectively partner swapping. So I'm going to have calcium go to phosphate and sodium go to chloride. So calcium goes to phosphate. And then just like these, remember when you're doing these, you don't have to write these charges, but these are the kind of things you want to have rumbling in your head while you're working on these. So it looks like we're going to need 3 calciums to 2 phosphates. So 3 there, I need parentheses, 2. If you think about it, there's a total 6 positive and then a total 6-. That way they balance out. We then go ahead and take a look at the solubility chart. And I'm actually going to blow this up a little bit just so we can clearly see what's going on. There we go. And excuse me, we have phosphate there on the bottom, typically insoluble. It's paired with calcium. So this is solid. All right, And don't worry about balancing it. You want to get the other one first. It's just going to be NaCl. Sodium salts. I recommend remembering that the alkali metals first group are typically soluble. So automatically AQ without looking at the chart. Okay, so we need to do some balancing here. So it looks like we're going to have, what are we going to have here? Remember, when you have the polyatomic ions, you can treat them as if they are an element. And I'm thinking we're probably going to put a 2 in front of the sodium phosphate on the reactant side. Excuse me, something in my throat. I need a drink here in a second. All right, 2, and then looks like we're going to need a 3. Wait, hang on a second. So that's going to give us 6 sodiums over here. Phosphates are now balanced. I'm going to go ahead and balance sodium now. So it looks like we need 6 sodiums on this side. Like that. And then I believe now if I put a 3 in front of this one, we're done. Yep, so we are now balanced. So it looks like we're going to get a precipitate of calcium phosphate. And I'm going to use that for a problem here in a second. Before I continue, are there any questions so far on how I got this reaction? I see that there are a couple of you guys in the Discord chat. So we're using the Discord chat for questions. You can just type it out. All right, I don't see any questions. Yeah, and if I go on, type your question anyway. If you're a little bit behind, I will still see it. All right, so now what I want to do is I want to go ahead and write the complete ionic equation. So it looks like, remember we break it apart. We have to account for subscripts and coefficients. So 2 times 3, we're going to have 6 sodium ions, 6 Na+. And then we're going to have 2 phosphates, 2 PO4, 3 minus. We're going to have 3 calciums, 3 Ca, 2 plus. And then same deal as we had with sodium earlier. We have a 3 coefficient and a 2 subscript. So we're going to have 6 chlorines. And then I like to make a second line here just because of how long these end up being, the long string here. So for the product side, we leave together anything that is solid or liquid or gas. Basically only break apart things that are AQ. So we're going to have calcium phosphate, leave it together, it's solid. And then don't forget your subscripts there, we have a 2. And then the other one we break apart, 6 Na+, and then 6 Cl-. Also remember, I'm shorthanding here a little bit. Technically, each of the ions should have AQ after it in the states. The homework wants that, so be careful of that. On paper, go ahead and shorthand. When I grade these, I'll be looking for, basically you writing out the solid is what I'm going to be looking for. All right, so now that we have the total ionic equation, we can cancel out spectators. So remember, you can kind of predict these by looking at the product side. These ones that are soluble on this side are often your spectators. That is also the case here. So 6 sodiums cancel, the chlorides cancel, we have this. And I like to rewrite this with the cation first. So 3 Ca, 2 plus, excuse me, 2 phosphates yields, and then the calcium phosphate. PO4, 2 solid, like so. All right, so we could ask, now that we have a balanced reaction, we're going to use that first reaction there for any kind of stoichiometry problem. Oftentimes you do need the entire compounds in there when working with stoichiometry. But what we have here now is remember this is called the net ionic equation. I like to use that for short for equation. This is basically, trimming the fat. We're focusing in on what reaction actually occurred. So let me go ahead and hide this little thing. We don't need that anymore. I do want to go ahead and make a problem. I'm going to show you how this problem will be presented in Chemistry 121. So far in this class, we've been working with grams for everything, or moles. It turns out in Chemistry 121, so in Chem 121, so remember this part's not going to be on our test. I'm just giving you guys a heads up on what's coming. We learned in that class that we have a term called molarity. This is a concentration. Basically, concentrations are how much you have per unit volume, similar to density. This is defined as moles per liter. And we're going to have to use this definition to answer the question the way that I'm going to present it. So I'm going to start a new page here, but we'll definitely be referring to that last page. So the question here is, how many grams of precipitate if 0.100 molar, so what this is saying is that we have 0.1 moles per 1 liter, and that's of the Na3PO4, and I forgot we need a volume here, so let's go ahead and say that we have 25 milliliters of this. So 25 milliliters of this is mixed with, let's go ahead and say we have 30 ml. Language. I'm online.
Sorry.
All right. So once again, the question is saying that we have, we have two mixtures that have this stuff dissolved. Remember, we know that these are soluble in water, and we're mixing this quantity together. So in Chemistry 121, you would have to do basically convert these to moles. It's not too bad. The way this works out is M is moles per liter, and then it works out where if you take mole, if you want to get moles, it is molarity times the volume in liters. So this term here is volume in liter. Okay, so I'm going to basically have the setup is the same as we did in the past, except we have this extra little step at the start. So I'm going to go ahead and set up here, and I like to remember I like to set up everything first before we break out the calculator, and then we will answer the question. Okay, so excuse me, we have to assume each one is limiting, and then we have to determine how much of the product, the precipitate product, we're going to get from these individual amounts, assuming they were limiting. And then what we do after we calculate that for both, whichever one gives you the lower number, that particular reagent is limiting, and then that amount that you get is your theoretical yield. So go ahead and set up here. So we have our 0.100 mole. So I'm actually writing out what molarity means. Mole of Na3PO4. That is per 1 liter of solution. We are starting out with, it says 25 milliliters, and we've seen this conversion in the past. We have that many liters of solution. And I'm using solution here because we're telling the reader that there are two things mixed together. All right, going to just slide up here. Hopefully you guys wrote that down if you're following along. At this point here, if you think about it, I am in terms of moles of Na3PO4. The liters have canceled. And then what I can do is use my balance equation to make a mole relationship between the sodium phosphate and the product, the solid product here. So it looks like the mole ratio is 2 to 1. So we're going to say it's 2 mole of Na3PO4 per 1 mole of the calcium phosphate. All right, and then the last step here is we are going to need the molecular weight of the calcium phosphate to get to grams. And we're going to do this as a side calculation. I'm actually going to need my phone here for a second. I showed you this app before. So let me turn this light off. I think the light's actually fine without that flashlight there. I'm just going to leave the flashlight off. I don't think we need it today. The lighting is okay in the room today. All right, so the app I showed you guys here was the EMD periodic table. And then here in the options, we have a molar mass calculator. And then all you do is type in the formula. Be careful, you need to type it in exactly right. It won't auto-correct your formula. So it is Ca3, we need parentheses here, and then PO4, close parenthesis, and then 2 of them, and then enter. So there's our calcium phosphate. It does percent composition, and it also does your molecular weight. So we're going to go ahead and use that number. Remember, you should know how to do this calculation by hand. This is actually on the last test worth of material. You just add up all the atoms and add all the weights. You guys know how to do this. I'm confident you know how to do this. So that's why I wait till this part of the class to start using the app a lot, because you probably don't need it shown out explicitly anymore. 1 mole of Ca3PO4. There should be a 2 in there actually. There's a 2. All right, that is our setup for the first part. Let me fix the zoom here. Yeah, it's a little bit off screen, but hopefully you guys can see it okay. All right, I'm gonna do the setup for the next one here. So it said that we had 0.2 molar. So that is 0.2 mole of the calcium chloride. And that is per 1 liter of solution. And then we, excuse me, the question stated that we had 30 milliliters, so that's 0.03 liters. All right, leave myself a little bit more space this time. Using the balanced reaction, I believe it was 3 to 1 for this one. Yep, 3 to 1. 3 to 1 is the ratio. So 3 mole of the calcium chloride per 1 mole of the calcium phosphate. So at this point in the calculation, they are the same. So the last step is identical for whichever one you start with. So this is going to be 310.177 grams of the Ca3PO4 2. All right, and that's per 1 mole of it. All right, we are set up for both now. So I'm going to go ahead and calculate for both and use my calculator. 8, there we go. All right, hopefully it's showing up okay. Yep, looks just fine on my end. So 0.2 times 0.025. This is how many moles of the sodium phosphate we have at this point. We then do a mole ratio, so divide 2. This is moles of the product, and then times 310.177, and then there is our final answer. So for this one, it is 0. Let's do how many sig figs should we have? Looks like 3 or like 2 sig figs, based off our numbers here. So 0.39, and then units here are grams of the product. And then this one for the next one, same kind of calculation. It is 0.2 times 0.03. This is how many moles of the calcium chloride we have. We then divide by 3. That's mole of the product. And then last step, to get grams times 310.177. And there's the answer for that one, 0.62. All right, so whichever one gives you the least amount, that is your theoretical yield. So this is what answers the question. How many grams of precipitate? It is 0.39 grams. We actually do this lab in Chemistry 121 lab, and you guys will mix the two together, and you'll basically collect the precipitate by filtration and dry it out, and get weights and all that fun stuff. All right. This other number here is meaningless at this point. We don't need this number for anything. It was just used for helping us get the answer. So the way it works out is whichever value led to this, that one is the limiting reagent. So limiting reagent. This one here is the excess reagent. And then this value here is theoretical yield. Let me just write it on the side here. Theoretical yield. All right. So I didn't want to go ahead and do an acid-base question for this one. And the question for this one would be, suppose someone spilt some acid in the lab, how do you clean it? and how much base do you clean it with. So let's go ahead and take a look at this one. So let me write out the question. So the question is, how many grams of baking soda would be required to clean a spill? Let's go ahead and say it's something like someone dropped a beaker full of this stuff. So they had 150, and I'll put a decimal there for 3 sig figs, milliliters of, and concentrated sulfuric acid typically comes at 18 molar, very concentrated, pretty nasty stuff. And it's H2SO4. All right, so in a word problem like this, I like to highlight things that are important. We're going to have to know what baking soda is. Let me use red. Baking soda is the common name for sodium bicarbonate, so NaHCO3. And we're also going to need this volume and this molarity and that compound. So this is the stuff we need. Starting this out, we need to actually write out an equation. Remember, this first part's going to require a molarity calculation. When we actually get to the calculation step, remember that you guys are not responsible for that yet. It's next semester, but everything after I get to moles, fair game for this class. So just this first little part that we didn't technically have as part of this course. Anyway, let's go ahead and do a reaction. So it's H2SO4. This is aqueous plus NaHCO3. This is also aqueous. We have a sodium ion. All right, this is going to act as a double displacement, so we're going to just partner swap essentially. But remember that we have the bicarbonate ion, which is HCO3 minus. This can actually accept only one more H plus. So I think last time we did carbonate, which take 2 more. This one can only have 1 more. So let's go ahead and, so one of the H's goes over. So this is going to be an H2CO3, aqueous. Remember this guy, we're going to keep something in mind when we start breaking things up here. And then what else do we have here? We have plus sodium bisulfate. It's a NaHSO4 for this one. We're off screen again. I did it again. Hang on, let me actually fix this drawing so I can get it all on screen. I need to get myself a little bit more width on this stuff, or just mark it, whatever. All right, so plus NaHSO4, and this is aqueous. Yeah, sorry about the eraser marks there on the video. I'm seeing it on my screen. So, all right. Okay, I believe we are already balanced. If you take a look here, we have 3 H's on this side, 3 H's. We have carbonate. We have carbonate. We have 1 sodium, 1 sodium. This is all balanced. This reaction will be a little bit different if you use sodium carbonate, which is Na2CO3, but we use bicarb here, so here's how it looks. All right, I'm going to go ahead and write out the net ionic equation, or complete ionic, then net ionic. But I do want to remind you that this is special here. This will decompose into H2O liquid plus CO2 gas. So when I do my total equation here, I need to actually include this in there instead, right? But I recommend balancing it from here, because if any coefficients go on here, they just carry over to both of these. So I think it's easier to balance from this perspective than you plug in after. All right, so only break apart things that are aqueous. So it'll be this one, and this one that we break apart. So let's go ahead and say we have, so the way this is breaking apart here, the way we're showing this, and I, oops, did it again, off screen. This is what's called a diprotic acid. We go over that in more detail in Chemistry 121, but this can deliver 2 protons, and it does it stepwise. So I'm going to show this as first the H plus, and then that. So it could deliver another one, but based off our reaction, it's only getting one. So that's how we're going to write it. And then Na plus, and then we have bicarbonate, break apart. And then this one, for real? Yeah, my phone's ringing already. Of course, everybody waits till I'm in class teaching before they start calling me. All right, so H2O liquid plus CO2 gas, and then plus this one we break apart, Na plus, and then HSO4 minus. So it looks like this net ionic is going to look really similar to what we saw last time. And just like before, this one here is probably going to be the spectators, just like we saw in the past. So sodium ions cancel, sulfates cancel, I believe, the bisulfates cancel. And then it looks like we have H plus bicarbonate gives H2O and CO2 gas. So I'm going to just write it here in the space so I don't have to move my face around or anything. So H plus HCO3 minus yields H2O liquid plus CO2 gas. So there's your net ionic. But remember, when you're going to be actually answering the question, you only need this one. You need the mole-to-mole ratio. I'm just doing extra practice from last chapter, so making sure we're getting plenty of practice here. All right, so now that we have this out of the way, I do want to go ahead and just actually answer the question now. And how many grams of baking soda do we need of this stuff to neutralize? All right, and I went and put you would actually dump it on there as a solid, but technically it's soluble, so this is fine to write it this way. But the math is going to work out the same regardless. All right, so let's go ahead and take a look at the problem now. Remember that if you have molarity and volume, multiplying them, you get the moles. So that makes a good place to start. So we have 18 moles of H2SO4. Here we go, 18 moles of H2SO4 per 1 liter of solution. I said that 150 milliliters was spilled. So 0.150 liter. We then use the balanced reaction for mole ratio. So it's 1 mole of H2SO4 per 1 mole of NaHCO3, sodium bicarbonate. And then to get grams here, all we need here is the molecular weight. And I'm going to use the app again, of course. I like using the app. All right, I still have it open from the last one. So I'm just going to go ahead and clear that out and type in sodium bicarbonate. So NaH, let me see that okay, it's kind of washed out. Oop, it's autofilling. I've actually typed it in here before probably. All right, so I'm getting 84.007 grams. So 84.007 grams of sodium bicarbonate per 1 mole of sodium bicarbonate. All right, you should always check units if you're getting used to all this stuff. So the liters cancels, the moles of sulfuric acid cancels, moles of sodium bicarbonate cancels. We have grams of sodium bicarbonate left over. That is what the question is asking. So always the last step is calculator. So very last step, 18 times 0.15 times 84.007. And I am getting 226. Take it to 3 sig figs, because honestly this would be a given value. That's a concentration of concentrated H2SO4. I'm going to add that little comment here. This is concentrated when it's 18 molar for that particular acid, and this is how much the student was actually carrying or spilled. So that was the amount spilled. That would have been the measured quantity. That would be go into sig figs. All right, so here we have 227 grams. All right. So the last thing I want to talk about here is I actually want to go ahead and take a look at the worksheet again to mention the last topic. So we're file, I think file multi, and then let me switch over to, I had a file open. What's going on? Not showing. Oh, there we go. Right, so I actually have some quick notes here that I wanted to mention. That you probably want to write these down or screen cap this at some point. But it turns out that earlier this semester we did talk about heat transfer between things that are hot going to things that are cold. It turns out that we also need to consider energy when looking at chemical reactions. So there are a couple things that can happen is if a reaction is giving off energy, we talk about the thermal energy of a reaction as being enthalpy. So we see enthalpy there. It should be right there. Enthalpy. It's the amount of thermal energy of a reaction at constant pressure, and it's defined as the heat, which was Q. Remember the letter Q per mole. It also turns out another big factor that's involved in chemical reactions and heat transfer is a term called entropy. Entropy has to do with random disorderliness. I'm not going to go into this in this class. You actually go over this in Gen Chem 2, second semester. Hi, Tristan. We're talking about entropy. What timing? Entropy just showed up. Random disorder chaos just showed up. What's up, buddy? You gonna hang out while I talk about this? All right, so there's two types of reactions that can occur, right, Tristan? Two types of reactions for heat transfer. One of them is it's endothermic, meaning that it takes the energy in. It means the required energy to go. You're gonna sit on my lap for a second while I talk about this. All right, we're gonna have two bobbling heads talking this right now. All right, so if a reaction is endothermic, it means it takes in energy, and then exothermic means it gives off energy. So a lot of reactions you can think of being exothermic are your combustion reactions we talked about earlier, with the balancing. I'm actually going to do a combustion for an example. But combustion reactions are useful. We call them that because they give off a lot of heat. We use them to power things, heat things up, that kind of thing. So here I'm basically showing, looking at the file here. You can see my mouse. Let me zoom in a little too so you guys can see it better. All right, a little better. Oh, you're falling. You're falling. Ah! Get your hand off the desk, please. Hand off the desk. Hands off the desk. All right, so we can treat the heat as a reactant or a product. And essentially, if it's endothermic, we treat it as a reactant. If it's exothermic, treat it as a product. It turns out that because we're treating them like that, we can actually treat them as reagents in stoichiometry problems. And that's what we're going to be doing in this class. So we're not going to be going over the calculation of delta H in this course. We actually go in full detail in 121, or at least we start it in 121 and then deep dive even more in 122. But for this class, we're just doing stoichiometry problems with heat considerations. All right, so I think the best thing to do is go ahead and look at our practice problem. So, and this is actually going to be the last problem for today's stream, guys. I'm actually going to cut the stream after this example. We are technically done with the entire chapter content at this point. We'll talk about that a little bit more after I do this problem. All right, so what I want to go ahead and take a look at now is the combustion of octane. And then we're gonna do a balancing, all that fun stuff, and then we'll go ahead and also do a stoichiometry problem with it, a couple of different steps. So combustion of octane. We don't go into detail in this course, but you guys will learn in organic chemistry later on, maybe a little bit in Gen Chem, that these are hydrocarbons. They have an A and E. They're called alkanes, their family that they're in. Oct is for 8. So this is actually how we name organic compounds. I'm just FYI for this point. And it turns out that alkanes, like the way you guys may be wondering, like during class, like how do they know how many H's there are? And it's basically, they have this formula, CnH2n plus 2. So the hydrocarbon, if the hydrocarbon is an alkane, you will have them in this ratio. So 2N is 16 plus 2 is 18. That is our octane. A little side note there. This is going to be a liquid. In order to burn them, we do need O2 in it. So we need O2 gas. And then remember, the products are CO2 gas plus H2O gas. And we're also going to have heat on this side as well. Remember that this reaction is exothermic, so I'm going to go ahead and put the heat on this side. These reactions give off a lot of energy. So this is exothermic, meaning it releases energy. And it's going to be heat energy in this case that we're going to be talking about. All right, before I start doing anything stoichiometry related, I need a balanced equation. So I need to balance this out. Remember that we did it in the order of C, H, and O. I know I have a lot of these examples in our stream, but these tend to be the hardest balancing problems for most students, are the combustions. So starting out, we have 8 carbons, we have, 18 hydrogens, and then we have, 2 oxygens. And then remember, this side always starts out as 1, 2, 3. For the sake of space, I'm going to do products right here. These are my product tallies right here. Okay, so to start balancing here, I need an 8 in front of carbon dioxide. That's going to balance my carbons, like so. I need a 9 in front of water to balance out hydrogens now. After you balance out your carbons and hydrogens, you want to retally the oxygens on this side. So it looks like we have, 16 plus 9, 25. All right, we have an odd number here to work with, so we're going to have to do fractions. Remember, you put in 25 over 2, and then you multiplied everything by 2. We can actually, so this is 25 over 2, that's going to go here. So multiply through by 2, it's going to be 2, 25, 16, then 18. I think we actually had this one. I didn't do this one in class, actually. Not in the stream. I think I did this one actually in class, our last day that we met. All right, so we do have a balanced reaction now. So the question I have here is starting with, let's say, I don't know, how much is 1 gallon of gas? So a gallon of gas is, so the question I'm going to do here is how much CO2 is released if 1.00 gallon of octane is combusted. I'm going to add an extra little part on here. So it turns out that when you're measuring quantities of gases, it makes more sense to use moles and volume than it does to use grams. But for what we covered in this class, I'm going to answer this in grams. And I will specify, when I write a question like this, when I say how much, you'll see the units in the choices for multiple choice, and then in a short answer, I will specify whether I want grams, liters, that kind of thing. For this chapter, I would definitely say grams. So let's go ahead and say grams here is what we're going to solve for. And then I'm going to do a liter calculation, show you guys like how this is, we add on to this later on this semester. We add on to this. All right, so one thing we need to know to answer this, we actually need to know what the density of gasoline is. The density of gasoline is about 0.7 grams per milliliter. All right, so we're going to do some conversions here before we can even start. So I'm going to do the conversions first before we do any setup. So we know that we have 1.00 gallon gas. So let's say octane. So 1.0 gallon of octane. We need to convert this from gallons to liters. I believe it was 3.785. Let me just confirm that. I'm pretty sure it's 3.785, but let me just double check. I don't want to do this incorrectly. So gallons to liters. Let me show you actually what I'm doing here, guys. So Google actually has a really great conversion tool built into it. Hang on, browser. Wait, browser full. Yep, so all I Googled was gallons to liters, and you will literally get a window popping up for a conversion chart. So yeah, you won't have this in a paper test, but you guys have your computers available, so here we go. So that's the conversion factor I'm going to use, 3.78541. Let's get all these different sig figs in there. All right, so let's switch back over to presenter camera. All right, so that conversion I need from gallons to liters was 3.785 gallons per 1 liter. Okay, I then need to get, we're going to use density to get grams. So at this point, we need to figure out or convert this to milliliter. So remember that it was 10 to the 3 milliliters per 1 liter. And then last step here, so this is all chapter 2 stuff here for you guys. It's all chapter 2 stuff here. So grams of octane per 1 ml. All right, checking my units here. Our gallons cancels out, liters cancels out, mLs cancel out. We have grams of octane left over, which is what we want. And this number would be what I would like, or this number can feed into the actual problem then. So you could make it all one long string with the stoichiometry also, but it's easy to get lost if you do stuff like that. So I'm going to do stepwise here. 1 divided by, oh wait, there's a mistake here. Yep, I made a mistake here, guys. It should be 3.785 liters per 1 gallon. So, oops. The units are still going to cancel. My number that I punched in my calculator are different. So 3.78541 liters per 1 gallon. They still cancel. We're still good. All right, so 1 times 3.78541, and then times 1,000 times 0.7, and I am getting this many grams. It's like 2.6 kilogram, but I'm going to put it in grams. So to 3 sig figs, 2649.787 and grams. And we are limited by 3 sig figs. I just don't want to round yet, so we want to round at the end. So, but we are limited to 3 sig figs here at this point. 3 sig figs. 3 sig figs. All right, we are going to need the molecular weight for octane. I'm going to, you guys know how I like to round hydrocarbons here. But anyway, I'm going to go ahead and set up. So 3649.787 grams of CHH, what was that, 18? I'm going to keep track of my sig figs here. We should have had 3 sig figs, but I'm going to use this whole number in the calculation. Set up there. All right. So then the next part here is for the molecular weight. We could use our app. Actually, let's just use the app. Get a better number for you. All right. So there we go. So CHH18, we clear H18, done. So my app is telling me that it's 114.229. 114.229. Yep. Grams of octane per 1 mole. All right. So at this point, we need to make a mole relationship between the two. I just had, where did my reaction go? Oh, at the top of the page of this page. The mole ratio looks like it's 16:2 for carbon dioxide. So it's 16 moles of CO2 per 1 mole of octane. So, oops, sorry, it was 2 moles. 2 moles. Okay, and then we're going to need the molecular weight for CO2. I'm going to use the app again. I think it's like about 44. I've done this problem a few times. Yeah, so CO2, yeah, it's 44.010. So 44.010 grams of CO2 per 1 mole of CO2. All right, there is our setup to get the answer. I'm actually going to write down this number here because we're going to use it for the next part. I'll show you guys how we expand on this for later in this course. So without clearing my I have that number in my calculator from earlier. I'm just going to hit divide, and that was 114.229 for the molecular weight for octane. And then I'm going to say times 8 because 16 over 2 is 8. So times 8. And then last step here is times 44.01. All right, so we're getting a lot of mass here. It makes sense to me because we're getting all these carbons bonded to oxygen now. That's a lot heavier than hydrogen is. So the increased mass here makes sense to me. So 8167 blah 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 grams, and then I'm going to go ahead and put this in the right number of sig figs. I believe it is 8170. It's supposed to be an 8 there. Grams of CO2. So there we go. Get the whole thing on the screen. There we go. So there is our setup. So here's our stoichiometry setup here. And there is the answer. And I said I was going to write this number down. Let me calculate that. I want to figure out how many moles there are because I was saying earlier that typically gram quantities don't make a lot of sense for working with gases. So I believe that was actually this number right here. So we had 180, let's say 186 moles of CO2. So if you were being asked how many moles of product we had, that would have been the answer for moles, and then grams is this quantity. Let me just double check that math. Oops. Yeah, that's right. Yeah, rounding issues now because of rounding, but yeah. All right, so that's the amount there. It is quite a lot. It makes more sense to talk about it in moles and volume. So this is a later discussion. I like to have it here though for the notes, just because it illustrates a point that when you burn 1 gallon of gas, a lot of CO2 goes out there. So let's go ahead and take a look here. So the equation we're going to be using, this is later in 103. We will go over the ideal gas law. This equation is pressure times volume is equal to moles times the R constant times temperature. And what I'm going to go ahead and do here is solve for V. And I'm going to make some assumptions here too. So V is equal to nRT over P. Typically here in Las Vegas, we are not at sea level. We are, above sea level here, so the pressure is lower than sea pressure. The pressure at sea level. So I'm going to go ahead and estimate we're at about 0.95 of what it would be at sea level. And the moles I got in the last equation was going to go in here. And let's go ahead and say, so the question is, how many liter of CO2 per gallon of gasoline if the temperature, let's say, we're a warm day in Las Vegas, it gets over 90 degrees all the time here. So not yet though, but it's coming. So let's say the temperature was 90.2 degree F. All right, so the way we need to, so we have to do one thing first. We have to convert this to Kelvin. So first things first. So to calculate degree F degree C from Fahrenheit, you take 90.2 minus 32, and then times 5/9. This is 32.3. And then we do this in Kelvin. I'm not going to go over why, but whenever we do gas law stuff, we work in Kelvin. and this is plus 273.15, and then final temperature there I'm going to use is 305 Kelvin. So that's roughly 90.2 degrees Fahrenheit. All right, so I'm going to go ahead and plug in. So V is equal to the mole quantity I had from the last problem, which was 186 moles of CO2. And then what we can do here is, oops, what am I doing? Hang on, I'm setting up like a stoichiometry problem here. Sorry. I can use the setup here. So it's 0.08206, that's the value for R. Liters, atmospheres per mole times Kelvin on the bottom. And then on the bottom also we're going to have pressure. So I set our pressure, we're going to assume it is about 0.95 atmosphere. And then our temperature we have to multiply on top here is 305 Kelvin. All right, so I basically plugged in for that over here. And for R, I put the units down here to show you how things cancel. So moles are going to cancel. Where's my red pen? Moles cancels, kelvins cancels, atmospheres cancels. We have liters of carbon dioxide left over. All right, so 186 times 0.08206 times 305 divide 0.95, and look at that. 1 gallon of gas gives you 4,900 liters. And people think that putting CO2 to the or burning fossil fuels is not affecting the atmosphere. Think about this: for every gallon of gas across all the cars across the world, this is having an impact. I don't care what anybody says. The numbers don't lie. So for every gallon of gas, you are putting in the atmosphere this much volume, and this is, assuming the temperature, gas contracts and stuff, so that's why we need temperature here. But in Las Vegas, per gallon of gas. So liters of CO2 per gallon of octane. All right, so I want to do one more problem here. I want to go ahead and figure out how much energy this would have been. We can do this. One thing we need to know is what the delta H of the reaction is. So let me go ahead and show you guys how I found this. So delta H of the reaction, this is the enthalpy. So this is reaction enthalpy. It turns out that if this number is positive, we say that it is endothermic, meaning it's taking in energy. And if this value is negative, we say that it's exothermic. This reaction is largely negative, and I found a website here that I want to show you guys. So let me go back to my browser. So what I literally looked up, hang on. Let's do browser full. There we go. So what I Googled was octane reaction enthalpy, and this page was like the first link. And I'm going to go ahead and use the one that's right here, saying here it's negative 1307.54, and there's like variance here too for their measurements. Heat per mole, remember there's a Q per mole. They're reporting their Q as K calorie. We can report it as kilojoule as well. This is going to work with kcals because that's the numbers here, but remember it could be joules also. It doesn't matter. It all depends on who wrote it. Really, that's all that matters. Thought I saw a question. Oops, there is a question. Yeah, Teslas are the future. Someone said Teslas are the future. I fully agree. I am hoping that within my lifetime, cars are fully electric and self-driving in my lifetime. We will save on pollution. We will prevent human death. We will prevent property damage. Think about how much death and destruction happens every day from car crash. It's a little bit different now. People should be at home, but during normal circumstances, there's a lot of car crashes every day, and a lot of CO2 pumped into the atmosphere because of cars. So yeah, self-driving and electric, I hope, in my lifetime. We'll see. All right, so I said I'm going to go ahead and use 1307 And then what was that again? Let me pull that up again. That was 1307.54. Let's go ahead and go with that number. 0.54 kcals per mole. All right, so when we use this particular reaction enthalpy, you need to also include mole conversions here too as well. So this is per mole. If we're going to convert this to mole to CO2, we need to actually consider the mole ratio inside of the reaction here. So it is we're going to use this number per mole. So heat released from the 1 gallon of gas. I'm going to go ahead and start my starting point right here. You could have also did moles of moles of octane, but I'm using moles of CO2 here. And that's what we started with. We're going to use this as a conversion. So I need to know that we have 186 moles, and this is going to be 1307.54 kcals. And I go back to the reaction. The reaction was 16 moles. So this is per 16 mole of CO2. So we need to make sure that we include that coefficient in there. Otherwise, our numbers aren't quite right. Typically, you're working from moles of the hydrocarbon, and you may notice here that they alter their number, or they alter their reactions so that they're all 1 mole in front of the 1 mole in front of the hydrocarbon. So let me pull that back up here so you can see what I'm talking about. Oop, yeah, so I'm looking at this part right here. Not sure if you're seeing it very well, but notice they have the half in there that we would have had, and that's to keep just 1 mole in front of that. So that's per 1 mole of octane, the way that this number is reported. So we have to account for that in our calculations here today. So let's switch back and just do the math. So it should be a lot of energy. That's what these reactions are used for. They power things like our automobiles. So we need a lot of energy here. And there is you might cover it in a later class, but you can go over, how many, like per carbon, that's a thing people do also, heat per carbon for the fuel. But there's my final answer. That's 15,200 kilocalorie. This is a lot. So we're burning a full gallon of gasoline. So 3 sig figs, 15200 kilocalorie. And if you wanted, you could do a joule conversion there, but we're going to go ahead and stop it here and say that this is the final answer for this question for how much heat was released. All right. Does anybody have any questions about anything from lecture today? We are technically done with the chapter and the exam content. We are now ready to move on. Hey, I gotta show this comment here. Yeah, what about cows producing methane? I know, yeah, climate change is complicated. I like to just look at numbers, and yeah, you do have things taking in CO2. You also have the other things contributing to CO2 besides hydrocarbons. But the thing is, anthropogenic CO2 production is definitely reality. I don't care what anybody says; it is not made up. Just the plain chemistry about it states that as you're burning this stuff, you are putting CO2 into the atmosphere. We are making sure that we're putting CO2 out there. That is the reason why you have smog checks, is to check that you're actually producing CO2 out of your tailpipe and not incomplete combustion products. And honestly, if we weren't doing that, the air would be even worse. If we had carbon monoxide and elemental carbon, unreacted hydrocarbons all in the air, it would be nasty. Yeah, so thank goodness we do smog checking here in the States. All right, so I want to talk a little bit about what we're doing now. So I think we have an exam scheduled for next week, I'm pretty sure. I'm going to post a quiz. It's going to be 100% multiple choice, just like it would have been in class. It's even going to be the same length. So I would have did 15 multiple choice. The difference here, it's going to be on Canvas, and it's going to be timed. I'm planning on giving you guys, I think I was planning on 30 minutes for the timed quiz. So as soon as you open it, boom, your timer starts. You better be ready. So I recommend that you treat it as if it were an in-class quiz. So study for it, and then you want to get your cheat sheet ready, you know, that kind of stuff, as if it were a normal class. You have the added benefits of having PowerPoints open too. Wink, wink, hint, hint. So yeah, I'm not going to be providing those charts for you because you do have access to them. So I think it's kind of pointless for me to post it again. So make sure you have your solubility chart, your periodic table, calculator. You're going to need a calculator, and all that good stuff. The exam is going to be the same exact format. It's going to be 20 multiple choice and about 2 pages of short answer. The way that's going to work, it's going to be actually 2 separate assignments. I have to break it up because of how you're submitting them. So the multiple choice portion will be just like the quiz, just like it is in class. You're going to do a multiple choice portion here, in Canvas. It's going to be timed. I'm thinking you're probably going to have 40 minutes for that because it's going to be 20 questions rather than 15. And you're also going to have a short answer portion which will not be timed. The short answer portions will be worked out on paper, and then you just snap a photo with your phone, and then you're going to upload it to a Word or PDF file. Hopefully you guys know how to do that. I will post a tutorial if you guys need to know how to do that. You guys should have access to the software needed via the school website. We do provide the software for you guys. Just capitalize on it now. You have access to the software on the school website through your student email. All right. So after you've done the short answers, and then you snap a photo, upload it to Canvas, and I will grade both as separate assignments. And the point values are going to be the same as they were as if it were a regular exam. So the multiple choice portion is going to be 60 points, and the short answer is 40 points. But there'll be 2 separate 60 and 40 point assignments out there just because it has to be this way. All right, guys, I'm going to go ahead and cut the stream here. We are cutting it, about 20 minutes early. Like I said earlier, I would have did group work today. I probably would have did actually a lot less work if it was in class. We did a lot of group work. These problems are in the group work packets. So with that note, I will talk to you guys later. I'll be on Discord here if you guys want to ask questions, but I'm going to go ahead and cut the stream right now. All right, guys, stay safe, stay home. Please stay home. It's defeating the purpose of the social distancing. If you're going out in public, you're going against it. You are spreading illness. Please stay home. All right, see you guys on Monday.